Thank you for attending this presentation. My name is Singh, and today I will be presenting on multi-mode quasi-static excitation for systems with nonlinear joints. This work could not have been done without the guidance of my advisor, Professor Matt Allen of the University of Wisconsin-Madison, and Robert Keither of Sandia National Laboratories. To begin, let's consider a structure with a single joint, for example, the one shown in our upper right corner. Throughout loading, we see that the interface between these two beams sandwiched together begins to exhibit slip. So if we take our attention to the figure on our right, initially, majority of the interface is held stuck, shown by red. And throughout loading, we see that the extremities begin to slip, shown in the color green. This is characterized by microslip, as in microscale slipping. However, we also have macroslip, which is global slipping. Both of these behaviors can be characterized by an amplitude dependency on our natural frequency and damping ratio on a mode-by-mode basis, as shown in the figure on our bottom left. This has been shown experimentally. For example, consider the S4 beam structure, which are two C-shaped beams sandwiched upon one another, and for mode 1, the first bending mode of the structure, we see this amplitude dependency on our natural frequency, and that regardless of our impact location along the beam or our impact force, these curves tend to overlay. And this should hold true for all modes of the structure. However, that is not always the case. Recent experiments have shown a case, for example, for mode 2, where the excitation of one mode changes the properties of another mode. So if we look at our figure here, our red curves denote what we would expect as single mode excitation for mode 2, and through exciting it at different locations as well as different amplitudes, we see the significant softening behavior that is due to the introduction of mode 1 to perturb the frequency and damping for mode 2. So then the question arises, what causes this behavior? We infer this to be modal coupling, which are nonlinear forces at the joints that couple single degree of freedom modal oscillators. For example, the oscillation of mode 1 could perturb the oscillation of mode 2 and vice versa. So this has often been regarded as a black box between these two oscillators, since such few models exist to capture these hysteretic systems. So since we can see this experimentally through the excitation of multiple modes, could we use finite element modeling to predict this, including friction at the interfaces? One method to excite multiple modes simultaneously is dynamic analysis. So here we have our finite element model of our S4 beam structure with 1.2 million DOF. It takes approximately 8 hours to integrate the response for a quarter cycle of vibration. However, to generate these frequency and damping with respect to amplitude responses, we need more than a quarter cycle of vibration, which can end up taking days to weeks to years. So it is unfeasible for such a structure. So rather than looking at the S4 beam, we will bring our attention to a much smaller structure, this 2D sandwiched beam. So it consists of two top beams that are cantilevered on one end and have a bolted connection on the other end. This is a 2D structure with about 8,700 DOF that we can run a dynamic analysis. So this 0.3 seconds will take about 24 to 36 hours to generate an amplitude-dependent frequency and damping response for the structure. An alternative to dynamic analysis is quasi-static modal analysis, or QSMA. QSMA can be used to find the effective frequency and damping as a function of amplitude in a much shorter amount of time than that for a dynamic analysis. This is done by first quasi-statically loading the structure in the shape of mode, and then letting it ring up for a quarter cycle to generate the quasi-static response. Using our force displacement curve, we can then generate our frequency and damping with respect to amplitude on a mode-by-mode basis. For the 2D sandwich beam, a dynamic response in this mode takes approximately 26 hours, whereas a quasi-static response will take about 2 minutes to provide the same information. This is the difference between 300,000 dynamic time steps versus 50 load steps for quasi-static response. The benefit of a dynamic response is you could say that we get a truth response where multiple modes can be excited simultaneously, whereas a quasi-static response is done on a mode-by-mode basis. So we propose multi-mode QSMA, QSMA, as an extension to quasi-static modal analysis that can excite multiple modes simultaneously and hence predict modal coupling by examining the interactions between these modes. QSMA is governed by the equation of motion shown on our left, where we excite the structure in the shape of one mode. Here, the shape is mode 2. QSMA, we just simply change this by exciting the structure in the shape of multiple modes, where red is mode 1 and yellow is mode 2, and we sum them to get our blue forcing curve. Unlike QSMA, where the sign is not important, multimode QSMA, the sign, since we're exciting multiple modes, is very important. For example, if we take these two modes, which red is mode 1 and yellow is mode 2, if both of them have the same sign on the mode, we have this in-phase loading, whereas if they have opposing signs, we have this much different shape, and we refer to as out-of-phase loading. To effectively show this multimode QSMA approach, this will be done on the 2D cantilever beam structure, where it is cantilevered on one end and has two beams sandwiched together. We will first run a dynamic analysis for 0.3 seconds, and this is done such that the modal forcing of these multiple modes is in phase initially. We will then run quasi-static modal analysis for a single mode excitation to generate our baseline QSMA results. Next, we will force the structure in phase and out of phase through our multi-mode QSMA approach, and repeat this at various amplitude ratios for both modes 1 and 2 as pictured below. To form the baseline for multi-mode QSMA and multi-mode excitation, we must first do single mode excitation using QSMA, as well as a dynamic analysis. For both modes 1 and 2, QSMA is shown in blue and our dynamic analysis is shown in red. There exists this difference between the red curve and blue curve, which we associate with numerical damping. The integrator introduces the spurious damping that is not amplitude dependent, but rather dependent on our time step, or specifically the ratio between the time step to our frequency of interest. By changing the time step, we were able to see various differences in our red curve. However, even at the smallest feasible time steps as shown there, it was not negligible. So for mode 1, we have about 0.02% numerical damping, and for mode 2, we have 0.13% numerical damping that we must account for when we do multi-mode QSMA. Now that we have a baseline for a single mode excitation, we will now run multi-mode QSMA as well as multi-mode dynamic case studies, one being a 10:1 prescribed amplitude ratio, and the other being a 2:1 prescribed amplitude ratio. The 10:1 ratio is where the dominant mode, in this case mode 1 shown in red, is excited 10 times as much as the amplitude of our subdominant mode, mode 2 shown in yellow. The 2:1 ratio similarly is where now mode 1 is excited twice as much as our subdominant mode, mode 2. The first case, 10:1, has the chances of having a low contamination from our subdominant mode, where our 2:1 ratio now has a higher chance for contamination from the subdominant mode. Here, our figures are shown for in-phase mode 1 dominance, but this will be repeated for out-of-phase mode 1 dominance and in-phase and out-of-phase mode 2 dominance. Furthermore, we will also run an in-phase dynamic response for both of these load cases, where initially we prescribe a 10:1 ratio and then let it ring out, and we also prescribe a 2:1 ratio and let it ring out for both mode 1 dominance and mode 2 dominance. It is assumed that the degree of numerical damping is constant for each dominant mode in our dynamic analysis. Now let's take a look at some results here where we have mode 1 dominant coupling. On our left, we have our low amplitude ratio where mode 2 is only 10% of mode 1, and on our right, we have our high amplitude ratio where now mode 2 is 50% of mode 1. We also see four curves where the black curves are in-phase and out-of-phase solutions for multi-mode QSMA. Our blue curve is our single mode QSMA, and our red curve is our dynamic analysis. What's interesting to see is for both low amplitude ratio and high amplitude ratio, our in-phase and out-of-phase solutions show a perturbation from our single mode quasi-static response, indicating this influence of mode 2 onto mode 1. Furthermore, we see that both in-phase and out-of-phase solutions form a bounding box for our dynamic response shown in red. To look more into that, we'll look at it at points A, B, and C, where mode 2 is 50% of the amplitude of mode 1, hence having more influence on mode 1. So here we have points A being early in our time history, B being in the middle of our time history, and C being at the end of our time history, where initially at point A we prescribe a 2-to-1 amplitude ratio for our dynamic response as well as our multimode QSMA in phase and out of phase. Later on in the time history, our multimode QSMA responses are still at 2-to-1, but our dynamic response is about 10-to-1 and 25-to-1 nearing the end of our time history. What this is due to is the increase in damping for mode 2, so only the response for mode 1 remains. And hence we see that at lower amplitudes, hence later in the time history, our dynamic response converges to our single mode QSMA. What is also interesting is that for multimode QSMA in phase and out of phase, these are at a 2-to-1 amplitude ratio, yet are able to capture, as in form of bounding box, for 10-to-1 and 25-to-1 amplitude ratios between modes 1 and 2. We can also look at this for mode 2 dominance, where on our left we have our low amplitude ratio, where mode 1 is subdominant at 10%, and on our right we have our high amplitude ratio, where now mode 1 is subdominant at 50% of the amplitude of mode 2. In both of these cases, we still see that the bounding box theory holds, where our multimode QSMA solutions form a bounding box on our dynamic response. What's also interesting to see is the bounding box is much tighter. It's much smaller than that for when mode 1 is dominant and mode 2 is subdominant. To look into that, we can look at points A, B, and C along the time history. Initially, it is prescribed such that mode 2 has twice the amplitude of mode 1. However, as the dynamic time history goes on, mode 2 actually becomes subdominant, where it has 1/3 of the amplitude of mode 1 at point B and about 1/8 of the amplitude of mode 1 at point C. This is primarily due to the increase in damping associated with mode 2. Nonetheless, we still see that our multimode QSMA curves form this bounding box, although the dynamic analysis is at the cusp of the in-phase solution at lower displacements. This is primarily due to the fact that these in-phase and out-of-phase solutions are at a 2-to-1 ratio. However, at that point in the time history, the dynamic analysis is actually at a 0.13-to-1 ratio. It's a very different ratio than we initially prescribed it. To conclude, we have seen a dynamic simulation for our 2D beam that shows a one-way transfer of energy between modes 1 and 2, where mode 2 has a larger effect on mode 1, but a little impact when reversed. What's interesting to see is that this multimode QSMA approach can also capture this effect by changing the size of the bounding box. The bounding box also provides a conservative estimate for the effective frequency and damping ratio of a mode. For multimode QSMA, it's important to note that these bounding boxes have a constant phase, so if we force it 10-to-1, it will remain 10-to-1 throughout the entire amplitude range. However, for a dynamic response, this phasing changes continuously, whereas we saw mode 1 or mode 2 was dominant, became subdominant later on in the time history. This MMQSMA, this offers a worst-case scenario conservative estimate with a dramatic reduction in computational costs. For the 2D cantilever beam, a dynamic would take about 24 hours or more, whereas a quasi-static response for all three in-phase, out-of-phase, and single mode took about 6 minutes. If we were to do it on a much larger structure, the S4 beam, dynamic could take up to months to years, whereas a quasi-static will take 24 hours. With that, I'd like to thank you and open it up for questions.